Hi, everyone. My name is Vijay Mahadevan. I'm from Argonne National Lab. Today, I'm going to be presenting about some recent work that we have done in comparing different remapping schemes for climate models. This is joint work with several researchers from Morhe at NCAR and Paul Ulrich from UC Davis, along with several other people from national labs. Let me get started. So there are several challenges in accurately doing solution transfer between unstructured grids. And it's, of course, a complex process. And then in the process, we need to ensure several critical quantities. One is conservation, so both global and the local sense of fluxes, for example. And the next is consistency. Can we retain higher order accuracy when projecting the solution from one grid to the another? And the next is monotonicity. Can we preserve the global bounds of the solution during this remap process? The next is dissipation, which is if there are local features in the solution as a function of the spatial profile, can we maintain those local bounds on repeated transfer, or do they dissipate away and you lose those features? The next is sensitivity, which is, is our remapping algorithm insensitive to the underlying unstructured mesh, or does it depend on the topology? There has been a lot of previous work along these lines for different multiphysics problems. We're going to be specifically focusing on 4 different implementations for climate modeling problems. One is from ESMF, which is the Earth System Modeling Framework. They provide both bilinear and conservative maps, first and second order. Next is Tempest Remap, which is a conservative, consistent, and monotone remapper. It produces linear maps for ensuring higher order conservative projections. And the next 2 methods are more meshless methods. One is the generalized moving least squares method with a global scaling for conservation and local bounds preservation as a post-processing step. And also we have the weighted least squares ENO method, which Jim just talked about. Here's a brief demonstration of our comparison. This is a one specific grid, the cube sphere to an MPAS type method, and we ran 1,000 remap iterations. And each remap iteration is transferring the solution from the source to the target and then back to the source. And that's one remap iteration. And we do this for 1,000 iterations, and we measure both the global conservation and the dissipation in the solution for one of the real fields. And we did this analysis for both synthetic and real fields. We measured order of convergence and dissipation and several other metrics that I'll go over in my actual talk. But this is just to give you a flavor of what's to come. So if you're interested in this talk, please attend the full live talk on August 12th at 1:30 p.m. This is part of the Component Coupling and Earth System Models mini symposium. And here is the address. See you there. Bye.